Okay. So first thing, perhaps I would like to discuss is the philosophy of the lecture. What I'm going to try to do during these 4 hours. So there is a vast literature on the subject. I've been asked to discuss symmetries of asymptotically flat spacetimes. There is a vast literature on the subject. My favorite reviews and papers you can find on the website, I think. And also you will have lecture notes that I wrote that I think the organizer will pass you at the end of the lecture. So this is a very classical subject. There is a vast literature, which means that there are very different ways you can try to lecture on this. So let me tell you what is my take on these lectures. I have 2 main goals, which I'm going to try to 2 things that I'm going to try to do. What I want to do is that I would like to introduce asymptotic symmetries in a way which makes it clear that it's not about a particular coordinate system. So perhaps you've seen BMS coordinate systems in the way in reading the literature, and I want to make it clear that of course it's there, but asymptotic symmetries are not about specific coordinate systems. They are something about a property of a class of spacetimes, which are asymptotically flat spacetimes, which I'm going to spend a bit of time trying to make this point very clear, hopefully. Which means that BMS coordinates will come quite late in the exposition. I'm going to try to construct definitions and ideas that hopefully will seem natural to you, and we'll see that we'll end up with the BMS coordinate systems and the discussion on them. Another thing which in my head is related is that because the literature is vast, also, I mean, historically there is this fact that in the development of the subjects, there were different schools which were working at the same times. They don't have the same style, and you can still find this in the literature. Especially, I'm thinking there is this whole school of related to BMS coordinate systems, related to the use of null geodesic congruence. Also, you have this the Newman-Penrose formalism, which is another way it's related, but different way of thinking about the problem. At least the formulas look different. So, but I think it's important for students in the field that, especially with this idea of celestial orography, I think it's important to have students to be able to read through the whole of the literature. So one of the things that I would like to do is, during the process of this lecture, get you acquainted with enough tools and ideas that hopefully will prepare you in reading this literature so that you can go for yourself and read the rest. Okay? So in this first lecture, I'm going to do a bit of this, and this first lecture is mainly going to serve as an historical introduction, trying to convey sort of what was the historical process that led to this notion of asymptotically flat spacetime. In the second lecture, I'm going to treat in a lot of details Minkowski space, and hopefully in a way which make all the rest of the discussions natural. So these first 2 lectures, they should be preparatory lecture for the core of the lectures, which would be the last 3 for the last 2 lectures. Okay, so this first lecture is about null geodesic congruence. So let's start with a definition. So first of all, so just something just to fix what conventions. So everywhere M and d mu nu is going to be a 4-dimensional Lorentzian manifold. And I'm working in signature plus, minus, 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 which is, again, not the same signature as Tim and Thomas, but no, this is the same signature, but precisely I'm not working with this one. Yeah, sorry. Okay. So definition. So null geodesic congruence is a fancy word, but precisely I want you to get exposed to this just to realize that it's just fancy, but it's simple notion. So if I have, so let L mu be a nowhere vanishing vector field. Then the congruence generated by L mu is just, so there are different ways of saying this, depends. So is the set of curves, so yeah, of curves it generates. Or in other words, it's the set of when it generates, well, yeah. So in other, or it's the set of trajectories of the vector field, or is the lines generated by the flow. So let me just draw a picture. We have a bunch of vector field. Well, you have a vector field and mu. Let's say something like this. Okay. So the congruence itself is the line. So do I have some colors here? Yes. So this is the vector field. The congruence is the line, the flow that the vector field is generating. So in this case would be this space of lines. Okay, so this is the flow. Flow, and so the equal congruence. So so the remark is that if you have is that L mu and another vector field f of x L mu, so if you just rescale the vector field, you gives the same congruence. Okay, so when you're talking about the congruence versus the vector field, you're just either focusing on the space of lines, the geometrical aspect of it, or the vector field itself, which on top, the vector field also knows the speed at which you're going along this flow. So then we have obvious definition. So a null congruence is so null congruence. This means that the vector field is null. So L mu G mu equals 0. And a geodesic congruence would be a congruence generated by a geodesic vector flow, vector field. Okay. Is there any question about these simple definitions? So why am I talking about null? So now we are I'm going to focus everywhere on a null geodesic congruence. So from now on, L mu generates a null geodesic congruence. Absolutely, yeah, this, exactly. It's another way of saying this, integral curves, trajectory. Yeah, thank you so much, thanks a lot. Yeah. So, why is this notion important? So historically, there was this idea trying to have an invariant characterization of the presence of gravitational radiation, because since the very first paper of Einstein, it was clear that you had gravitational radiations in the linearized theory. A question in those times, in the 60s, was, can we give a nonlinear characterization of the presence of gravitational radiation? And one idea that came along, so there is a bunch of names that I need to write at this point. So the idea was that historically, you have people like Pirani, and I'm going to forget names, but also Trotman was important, Sachs, etc. They had this idea that one idea to characterize the presence of gravitational radiations was the following: was to follow. You take a null congruence of geodesics. You follow this null geodesic congruence for an infinite amount of time, so you're going to infinity. But because you're following a null congruence, you're going to infinity at the speed of light. And the idea was try to follow the gravitational fields, meaning the Riemann tensor, and try to understand how it behaves as you follow this null geodesic congruence. And the idea was that because the gravitational waves you should expect that it goes at the speed of light, you should know as you go along this null geodesic congruence, you should capture something of the presence of the gravitational waves. So idea, investigate, and this was a very deep and profound idea that really unlocked many results there. So investigate gravitational waves by studying the behavior of gravitational field by which you should really think Weil tensor along as one follows a null geodesic congruence. To infinity. Okay. Very good. So this was very important, and we'll see some. I will show you some essential idea of what people did at the time. Yeah. Another thing later on, and this was BMS later on. So BMS. So by BMS, they are. So I'm going to use this word many times. So So this is Bondi, van der Berg, Metzner, and Sachs. They realized that it's much more. That it's very useful. Well, it is very useful to study something which is not a generic null geodesic congruence, but an hypersurface orthonormal geodesic congruence. I'm going to explain what this is. To study Okay, so but before I do this, now I'm going to introduce coordinate systems to give you a practical flavor of what this is about. So one of the reasons, again, so and we'll see this several times. One of the reasons I'm talking about this, one of the reasons it's useful, is that null geodesic congruence are associated with coordinate systems, which so depending on what, in particular with BMS coordinate systems. So let me do this. So if you want proposition, so consider null geodesic congruence generated by n mu. One can always find at least locally a coordinate system so this is going to be, so I have 4 functions, u, r, and something which I'm going to write as ya. So these a's, they go to 1 and 2. So depending on, so depending on the context, this is going to mean different things for me. So sometimes would just be, sometimes it would just be 2 real numbers, and sometimes ya, so y1 would be some z and z bar holomorphic coordinates, depending on what we care about. So it's 2-dimensional, so you can go from one to the other. Okay, and such that what? Such that, well, the vector field L mu, so how should I write this? L mu dx mu is just dr, and ds squared has the following form. So hopefully I will have enough room here. Well, wait. Let me write this here. Well, no, because I'm going to pollute the definitions. Okay, let me erase that, because otherwise my metric is not going to fit on the wall of the blackboard. Okay, such that this one, so this, so L equal d over dr, and ds squared has the following form. So there's going to be some v function of u, r, and ya, du squared plus 2 du dr plus curly h ab u r y's of dya minus u a u then there is also a last term, which I'm going to write with a curly d. dya dr. Okay. And also, so here V, H, D, and U as well, they are function on all my coordinates. The fact that it's null geodesic, so you see dr, dr, there is no dr squared term, so it's null. And the fact that it's geodesic, it means the following. That the d coordinates, the curly d, actually cannot depend on r. So it only depends on U and YA. Good. So what's the picture? So R here is my time flow. So let me hide this thing. So this is. I'm not going to prove how to construct this system of coordinates. There is a proof in the notes that you will get. But here's the essential idea. You take some hypersurface, which is going to be your initial times, r equals 0. Your vector field, you take this surface to be transverse to the vector field. You choose the coordinates along r to be u and y's. So u and y's, they are coordinates on this initial hypersurface. And then you just flow along the vector field, and this is constructing for you the coordinate system. So then at other times, I have these are slices of constant time. So one way to think of this is that if you have a null geodesic congruence, it defines the time for you. So if you have an initial slice and choose coordinates on the initial slice, then you're producing this type of coordinate system. So I should write this. So if this is sigma, so the r equals 0. What do I have? Yeah, I have these blue lines, they are u equal constant. And you transversally says you have YA equal constant. Okay. So this is how you do it. You take your initial surface, choose a system of coordinates u and y on sigma, and then you just flow along your null geodesic congruence, and you construct a coordinate system. Okay. Yes?
Can I ask, what separates U from Y? Anything at this stage? Or
Right. So I think at this stage, there is no preferred. So we can. Okay. Let's look at in the metric what is going on. So I think at this stage, nothing is making U different from Y. It's just some funny way of doing it. But now I'm going to impose a condition which is going to give some different role to U. Well, actually, let me check. Yeah. At this stage, they are playing the same role. But I'm going to impose something that are going to give them some different role. Yeah. Thanks a lot for this question. Very good point. Okay, so remark here, if you compute the following object, so L, so you lower down the indices of your vector field, then it's du plus dA dya. Why do you want 1/2?
I didn't write 2 times d.
Right. Okay. Yeah. Thank you. Yeah. So now we are going to look for special type of null geodesic concurrence. So you see, at this stage, why am I writing this? I'm writing this because what do you want to say here? Yeah. So well, now you'll see in the definition. So a null geodesic congruence is hypersurface orthonormal if there exists a function u such that what we would like that L, this object here, so L mu G mu G x nu equal just du. So yes. This will make you very special, and this will make also the nudge of the congruence very special. Because now, so let's just see that the definition makes sense. So now our L really is orthogonal to the surface u equal constant. Because if I have x mu d mu u equals 0, d mu u equals 0, so this means that u x is tangential to these surfaces, then indeed x mu L mu G mu nu, well, by definition this must be just du, so this is just x mu d mu u equals 0. So indeed, L now is really normal to these u equal constant surfaces. So I don't know if I can. Yeah, so now in this picture, what's going on is that this u equal constant slice is in there. So now I'm going to have trouble with my colors. So now, yeah, I should not have used blue here, it's bad. What can I do? Yellow, green, whatever. Red, no. Oh, I don't know, maybe white in the end. So this u equal constant slice, they are like this, they intersect. Or something like this, you have u equal constant slice, so let's say this is u equal constant. And what is strange here, you have to get used to it, is that L mu is at the same time normal to u equal constant, we prove it's normal to it, but at the same time it's along these surfaces. Okay, so you have this r equal this slice of constant time, and then you have this slice of constant u, and the vector field is along this constant u surfaces. So anytime you see now this, what this is imposing also is that it's killing the d term here. So okay. Yes, I want to be very clear on this. So what's the other remark? Yeah, so this was the first point. The second point is that the surfaces u equal constant, they are null hypersurface. And so L mu is both tangential and normal to u equal constant. Okay, is there? Now here it's. Now I'm changing this proposition. This is hypersurface orthonormal. So what have I done? So at the end of all this, what we now see is that if you start with a null geodesic congruence, which has this property that it's hypersurface orthonormal, it's also the same as non-twisting, then you have this coordinate system associated with it. And if you know BMS coordinate system, these are exactly coordinate systems that are of these types. And yeah, these are called Newman-Munti gauge typically. So in other words, anytime you see this type of coordinate system, what is behind is that you've chosen a null geodesic congruence going through your spacetime. Okay, and the proofs for the existence and everything of this stuff, I put some details in the files. Yeah, and also one thing is that you should be aware that this is a constraint. Not every null geodesic congruence satisfies this property. This is some very specific type of null geodesic congruence that you're choosing here. They are the non-twisting one. Okay, is there any question on this aspect? No? So the point is that we are going to see many times this set of coordinates appearing, and I want you to keep in mind that it's not just coordinate system, but what's going on geometrically is that anytime you see this, you have this congruence of null geodesics which are going to infinity. Yes?
The condition for the curves that satisfy this condition, does it depend on the choice of the vector field we choose or the choice of the coordinate system?
No, this is a constraint. Okay, very good. Then I should write. This is a constraint on the vector field. Yeah, it's a good point. So you can maybe proposition if you want. So I wrote this in the file. So L mu is hypersurface orthonormal. This is a constraint on the vector field. This is this constraint. So let me just not write it wrong. So yeah, thank you for the question because I was about to skip this, but it's clear that it was a bad idea. So this is the constraint. D mu L rho equals 0. And this square bracket, they mean complete anti-symmetrization. Okay, so it's a condition on your vector field. That's what it is. So the reason why I try to explain in the file, this is essentially Frobenius theorem. That makes it works. But yes, it's not a constraint it's not about coordinates. This is really a constraint on the type of vector field that you're considering. But then it means that when this is true, then you can construct this coordinate system where u plays a very specific role because y's, they don't appear here. This term does not appear. Yes?
Could you give a bit more detail why DA vanishes?
Okay, so many ways of doing it. Either you take this coordinate system and you compute, you believe this theorem, and you compute this guy, and you will see that this will force this object to be 0. Okay, so either it's a computation, or you see in this definition, this usually definition here is really that you want, when you contract L mu inside the metric, it should just be du. But L mu is dr. So when I contract it, what are the terms which appear? Well, there is just this du term, and then there is this one. But I don't want this term because I just want du. So that's why it should be 0. Okay? Good. Any other question?
Can I ask another dumb question? Maybe
Please, please, please.
Like, I don't know, like instead of like, say, a torus or some sort of double null coordinates, like at what stage do you, like, could you try to be more specific and make like, like look at congruences of like the radial coordinates being null and then like another.
Null coordinates.
Yeah, versus like with weighted boundaries.
So I guess your question is, if I have null geodesic congruence, can I always construct a doubly null coordinate system from this? Yeah, we need to think about it. Yeah, I can't answer. Maybe someone in the, they are experts on null geodesic congruence. You know, okay. Well, we can discuss later on. I can't answer like this. I would, yeah. I would say no, but maybe I don't know. Yeah, I would need to think.
What is the question?
Oh, no, I was
The
just-
question is, yeah, the
you
question.
presented a very systematic presentation of like the Bondi story, and then I was curious, like, what would happen if instead of wanting to, you know, like, if the goal was to, I guess, have a coordinate system adapted to either going radially null or along scry in a transverse way, like if there was a change to the step that would let him do that.
Okay, so let me rephrase that. So U and R, in this picture, they play a different role. R is null, but U is not null. So in this coordinate system, U and R, they sit on different footing. There are typically coordinate systems which are used in the literature are doubly null coordinates. So let's say UV, where both null vectors are null. The question, perhaps the question is, suppose you have null geodesic congruence, can you always construct a doubly null coordinate system associated with this? It's probably quite, I mean, it's quite straightforward question, but I know, yeah, we can sit down and do the computation to check.
I don't know. If there is some other symmetry, like spherical symmetry, then it's easier. But in general case, I'm not sure.
Can we start with a no hypersurface and then there is a vector field which is orthogonal and tangent to it, and then we could construct a vector field which is also null and which and inner product with this first null vector field will be, for example, -1.
Yeah, you would like.
And then we could maybe parallel transport this this vector field. Then we can at each point of the null hypersurface we will get a null geodesic which has tangent vector, which is this second null vector, and then we can parallel transport this first vector field along this second one and then construct it.
Yeah, I think that's one way. Yeah, I think you're right. I think it's one way of thinking of it. Yeah, maybe so probably yeah. Some construction. I mean, yeah, some construction like this should work. Yeah, I think you're good. I think this is correct. Yeah. So yeah, I'm not saying that, of course, rephrasing this, I'm not saying that this is the only coordinate system you can construct. It's just that this is typically one that you might want to use. Okay, so now this we have coordinate system, but remember the idea was we want to understand behavior of fields along this null geodesic congruence. So in order to do this, what you need is null frames. So what I'm going to do, yeah. So we want to compute some invariance of this congruence. So we need a bit of tools to do that, to construct stuff. So we will need null tetrade. So a null tetrade is a frame so let me just write a block what I mean here again. So here, L mu and N mu, they are real, but M mu, I'm going to write this as M1 mu plus I M2 mu and M bar as the complex conjugate. So such that, so you want the following condition. So all contractions are zeros. But L mu N mu G mu mu equal -1 and M bar mu M mu G mu equal 1. So in particular, L squared equal N squared equal M squared equal M bar squared equals 0. So this is why it's a null tetrade. And if I'm writing this as alpha, I have that M alpha mu, M beta mu equal delta alpha beta, where this alpha beta is 1, 2. So it's in general, it's a very, so probably you're what's that? Well, probably you're used to frames. So choose orthonormal frames, which you choose frames which form an orthonormal basis. Another very useful notion is null tetrade, which are a frame with all of the vectors they are null. I think we'll see this many times during this week. It's a useful notion in many contexts. And so the point is that when we have a null geodesic congruence, we already have a null vector field, which is chosen. So then we can construct null tetrade which are adapted to the null geodesic congruence. So let's see how many of them we have. So proposition. So let mu generate a null geodesic congruence. Let L mu M alpha, so now I'm going to use M alpha mu N mu be an an adapted null tetrade. Here it's adapted just because I'm choosing one of the vector in my null tetrade to be the vector that I care about. Okay. Then the question is how many of these null tetrade we can find. So then there are not that many. Then any other null tetrade, which I'm going to write with an at. So this one is the same because it's, I start with my null geodesic congruence. I have a null vector field, so I want to keep this one. And then I want to change null to null tetrade. So, okay, no, it seems that I rather use this bar notation. Then any other null tetrade, which I'm going to write with an at, must be of the following form. No, the L should be the same. Okay. Because that's the point. You start with a null geodesic congruence. So you want to look for null tetrade, but L is fixed because it's part of the geometry you want to care about. So we want to construct something from the null geodesic congruence. So it stays the same. Must be related by, and you can convince yourself this would be an exercise, that there are none, it must be of the following form. So m sharp at is just m, so the original m plus f of x, certain function, complex function, L mu. And then this is the only free data because n at mu, in fact, is of the following form. So it's n mu plus f of x m mu plus f bar of x. This is okay, good. Yeah. So this x? Yeah. They are just the function on spacetime. So I just want to say that this is any function on spacetime. So maybe I should write it here. Yeah. But so you see that there is not that freedom in choosing the null tetrade. So once you've chosen, basically what's happening is that once you've chosen L, well, there is not that the tetrade is almost fixed. All you need to choose is M, and there's just one parameter of function that one free function in this choice. Okay, and I will let you. This is So you see, this is the point. So M is defined up to addition of L. But then, once you fixed M, it fixes this function f, so it's completely fixing n. This is what you should have in mind. So why is this interesting? Because now we can construct invariants of the null geodesic congruence. We can keep the definition here. Yeah, please. Okay, you also have the complex conjugated one. Yes. Yeah. Oh, sorry. Absolutely. No. Yeah. Okay. Yeah. Thanks a lot. Yeah. This is bar. And there is also the complex conjugate here, but which I'm not writing now. Was that your question?
And like which one from these equations that's going to be just m bar?
So this is m. I'm not writing, okay, there is also a transformation rules for m bar, which is just take the complex conjugate for this one.
Oh, okay, the bottom one is n, never mind.
Yeah, this is m and this is m bar.
Okay.
Is that fine? Is that okay?
Yeah, I just misread the...
Yeah, very, yeah. Yeah, this is n, this is m bar, this is m, this is m. Yeah. thanks for the question. Okay. So again, you have your null geodesic congruence. L mu is fixed. M is almost fixed, but it's fixed up to addition of L. And we are going to use this to construct some invariance of the congruence, so corollary.
May I ask one question?
Yeah, please.
Because there is the condition for the mutation
Yeah.
for the product of L with n to be -1, right?
Yeah.
Then I was wondering if there is no condition coming out of this constraint.
Very good. So let's check.
Yeah,
So L is the same as before.
yeah, exactly. But
So-
then if
So let me contract. So I'm contracting L with n hat. But by construction, L is null. So this last term is not contributing. But L is also normal to M. So I didn't write it, but L dot M is also 0. So all these terms here, when contracted with L, they disappear. Right? So L squared equals 0, but also L dot M equals 0. Right? So that's indeed it's one of this is what makes this result work is the funny property of a null frame, which are somewhat. It's a different type of intuition. We are really working with null vectors, so it's slightly different type of intuition than what you might be used to. Okay, so what I want. So let M G mu nu. I'm going to be a vacuum solution of Einstein. With lambda equals 0. Let L mu generates a null geodesic congruence. Well, then you can compute the following object, which I'm going to call psi 0. So this is the following. So it's psi 0 r mu rho sigma L mu M mu L rho M sigma. And this is a complex number. Is an invariant of the null geodesic congruence. And invariance here, I mean that it does not depend on anything, does not depend on the choice of M. Okay, when you write such formulas, you might wonder, okay, but M is not unique, so depending on the choice you're making, you'll get a different answer. But it's not, because the Riemann tensor is Q-symmetric. So if there is the ambiguity in M disappears because it's killed by this other term. So really, this object is called this is called the Newman-Penrose coefficient. Is something which is it's some invariant property of this null geodesic congruence. So there are many games similar to this that you can play, construct some invariant objects related to this, related to a null geodesic congruence. So let me write a bunch of them here. I have 5 minutes, so I need. Let me. So in which order do I want to say this? Yeah, I should say the reason why I'm imposing Einstein's equation is that really in the classical literature, Newman-Penrose coefficients, they are defined in terms of the Weil tensor here. But because I am posing Einstein's equation with zero cosmological constant, this is really the same. So I can use the Riemann for the Weil without thinking. That's why I'm doing this. So yeah, let me keep going with the Newman-Penrose coefficient. Then I will discuss. Yeah, I will just have time to discuss this. So of course, it's not the only object that you could have constructed from the Riemann tensor. There are other guys. So what about the other? So you see, this one is an invariant. There is another guy that you could have constructed, which is the psi1 Newman-Penrose coefficient, which is, so it's a definition. Huh? These objects, they are definition form. So there is this psi1, which would have been something like this. Mu m mu L rho n sigma. This is again a complex number. So you see, in general, this object is not strictly speaking an invariant object because there is an ambiguity in this n, and if you change n for another one, well, this part does not contribute because it's contracted with a skew-symmetric tensor with an L, but this part would contribute. So if you change n, it's going to change this psi1 by a term which is LM, which is going to change, which is a term like this. So if psi0 is non-zero, this object is not strictly speaking an invariant object because if I change my nullity trait, it's going to change this one by a term like this. But if psi0 equals 0, then this object becomes an invariant. And you can play this game several times. So now, if psi0 equals psi1 equals 0, then there is another guy, which is psi2, which becomes an invariant. And this, you see where the number is coming from, because there is this tower of relationship. So psi2 is R mu rho sigma L mu. Sigma is invariant, and then you continue like this. So now, if the three are zeros, then there is another guy, and I'm not going to write them all. You can find on the internet. So these objects, they are very classical. You go on Wikipedia. If you don't remember, you go on Wikipedia, Newman-Penrose coefficients, and you immediately find. I think there is a nice Wikipedia page that has been written down by, maybe not Wikipedia, but Scholarpedia, which has been written down by Newman, I think, which is very good. Also, I like Tim and Newman reviews on null geodesic congruence. Yeah, so there is something which is called psi3 which becomes invariant, and then if is the 1, the 2, and the 3, they are all zeros. Then there is another guy called psi4, which becomes invariant. So you see, this is how you think, how you use Newman-Penrose coefficient, is that the numbers here, they are trying to help you remember which one is invariant and in which order. You choose a null geodesic congruence, this guy is invariant. If it's 0, then psi1 is, etc., etc., etc. If all of them are zeros, including psi4, your spacetime is just flat. So it's not very useful.
Can I
Yeah,
mention that?
please.
So, for example, I would have thought, going back to the question about like null congruences, normally if you're at null infinity, you're also interested in like the congruences that along null infinity. And so these things vanishing, to what extent can you say they vanish strictly at scry?
Okay,
And then you're saying
I'm coming here. I'm coming to, at this stage, I'm not talking about scry.
Yeah.
I'm coming to, this is like last minutes, this is where I want to go in this lecture. So let me say something. So, yeah.
Sorry, the vanishing of psi0, does it imply the vanishing of the R, L, M, L, M bar? Because you need that for
So I mean, this is a complex number. So first thing, this is a complex number. So if this one is 0, you can complex conjugate, and you also it means that the bar one is 0. Yeah. Right. Right. Then it's true. It's not obvious. So I leave you at an exercise to check. These type of things you need to use. You need to use the Bianchi identities. So you see, the claim is that in the Weil tensor, there are only 10 real components which are independent, 5 complex components which are independent. So the other guys that you're talking about, it should vanish indeed. You need to check that this is equivalent to this guy vanishing. Okay? So it's an exercise. It's not obvious, you're right. It's a good point. But again, the reason why it works is because naively there are many components in the Weil tensor, but because of Bianchi identity, many of them, they are just the same. So in fact, at the end of the day, there are only these 5 complex numbers, psi 0, 1, 2, 3, 4, which are independent numbers which are defining the Weil tensor. So that's why I'm saying if all of them are zeros, then it's completely 0. And then you should ask the same question, what about this other guy? But I'm telling you, they are already taken for. Okay, so it's a good question. It's an exercise to check that indeed this is working like this. Yeah, so the idea of Sachs. So now, Sachs, I want to finish on Sachs peeling, just to give you. So all of this is again, there are 2 things. One thing is to give you a flavor of what type of ideas people had back in the beginning of the subject. Also, once again, to get you acquainted with this object so that when you meet them in the literature, you're not afraid and you can keep going and not just close the paper just because there are some funny notations that you've never seen before. So let me just come to Sachs peeling. So Sachs had this idea. So these guys, they had this idea that first of all, maybe you can think of gravitational radiation as being related to the behavior of the Weil tensor. And Sachs had this idea that one way of thinking of gravitational radiation should be you follow a null geodesic congruence like this, you go along the null geodesic congruence, and you try to see how these guys behave as you go along the null geodesic congruence. So for example, you'd like this psi 0 is some invariant object, so you'd like to his idea was to characterize an asymptotically flat spacetime by requiring the following feature. So psi 0, again, is the invariant. So what about how does it behave as r goes to infinity? And it seems that it was a good idea to ask for the following behavior. It goes as r minus 4 plus minus 5, sorry. Then this guy goes to 0. So if this guy goes to 0, you go for the next invariant, psi 1. And then you can ask that it goes to 0, but slightly slower. And then you keep going. At each order, if the component becomes an invariant in a row, and you can ask for a slower fall-off, -2, until psi 4, which is the last one, which is the guy falling off the most slowly. Okay, and again, what's important is the order. They have this order because they become invariants of the null geodesic congruence in a row. This guy falls off very fast, and the psi 4 is the one which last for the longest time. There are many ideas around this. One of Sachs' ideas really was that this was imposing some sort of asymptotic exceptional, what we were discussing before, exceptional algebraically special condition on the Weil tensor. Yeah. So this was imposing some special algebraically special condition on the Weil tensor. So this is like asymptotically type n, but I don't have time to discuss this type of intuition or ideas. And so you see, this they all turn to 0. This is this is the guy which is falling off the slowest one. So this object, when I will finish on this, in this way you can think of this as gravitational radiation. This is the field which is getting, so this is sometimes called the gravitational field. Okay. There are other, I'm already, there are other invariants such as the shear, the twist, etc. I wrote the definitions in the sheet. Where I wanted to come from is that this was sort of original set of ideas. You go along null geodesics, you look for the way this Weil tensor behaves, because it's clear it's some natural ideas that you have in the setup. What I will show you in the next lecture is that, and that's what sort of Penrose, at least from my perspective, brilliant idea is that you can recover this behavior from a much more very natural definition, which is asymptotically flat spacetime. And this will be, hopefully, I will have time to go to this at the end of the fourth lecture. Okay, that's it. Thank you. Microphone.